Hello everyone, I am Sagarika Tripathy. I am a PhD scholar at IIT Madras, Chennai. I'll be talking about the generation of primordial magnetic fields during inflation in models involving deviation from slow rule. The outline of my talk goes as follows. I'll be discussing the observational evidence for magnetic fields from different telescopes like Fermilab and HESS. Then I will talk about the generation of primordial magnetic fields and the construction of coupling function for slow rule inflationary models and models involving deviation from slow rule that leads to features in the scalar power spectrum over large scales as well as over small scales. Then I will talk about the challenges in the generation of primordial magnetic field in single field models and how we circumvent those challenges with the help of two field models. Lastly, I will talk about the imprints of the primordial magnetic fields on cosmic microwave background. Then I will conclude the talk with a brief summary. Well, in galaxies and cluster of galaxies, the observed strength of this magnetic field is of the order of microgauss, which has a coherent length ranging from kiloparsec to megaparsec. In intergalactic medium voids, this strength has a lower bound of 10 power minus 16 Gauss and it is coherent on scales above 1 megaparsec. Well, these magnetic fields can be produced by the amplification of pre-existing weaker magnetic fields that we address as seed fields by physical phenomena like dynamo mechanism. Well, these seed fields can either have astrophysical or cosmological origin. So now, since these IGM magnetic fields are expected to be in their undistorted form due to absence of any plasma or magnetohydrodynamical processes, so we are interested in the constraints on these particular magnetic fields. Well, as you can see here, this is a plot of the observed strength of the magnetic field today as a function of the co-moving length scale lambda. Now, this orange shaded region represents the bounds on the large scale magnetic fields. So this upper bound, which is of the order of 10 power minus 9 Gauss, it comes from the CMB data and the Faraday rotation measurement of the radio emission spectra from quasars. This lower bound, which is of the order of 10 power minus 17 Gauss, it comes from the GeV photons from blazars. Well, these large-scale magnetic fields could have been produced during inflationary epoch of the early universe. Now let's understand how magnetic fields can be produced during inflation. Well, during inflation, magnetic fields can be produced by breaking the conformal invariance of the standard electromagnetic action. Now here we have presented a general form of the electromagnetic action where these J phi and I phi are the coupling functions which break the conformal invariance and they couple the inflaton field with the electromagnetic field. So the second term is a parity-violating term which induces helicity in the electromagnetic field. Now, varying this action, we can arrive at this equation of motion and obtaining the stress energy tensor from this action, we can get these forms of the magnetic and electric spectrum. As you can see here, these magnetic and electric spectrum include both positive and negative helicity modes. So for gamma is equal to 0, that is when we need non-helical fields, we will see that these modes evolve in a similar manner. Now let's understand how the coupling functions can be constructed and how the corresponding spectra will behave. So if we work with a coupling function which goes as the power law of the scale factor, we obtain a scale-invariant magnetic spectra for n is equal to 2. Now here we have presented the forms of the magnetic and electric spectra for both non-helical and helical fields. So as we can see here, the non-helical spectra differs from the helical spectra, that is the magnetic spectra, by a factor of f gamma. Now, if since we have worked with the value of the helicity parameter gamma as 1, we get f gamma of the order of 10 power 3. That is, the difference between the non-helical magnetic spectra and helical magnetic spectra will be of the order of 10 power 3 for gamma is equal to 1, and the amplitude of electric and magnetic spectra for the helical fields will be same. So now let's understand what kind of coupling function we can construct for slow roll models and the corresponding behavior of the power spectra. Well, we can write the coupling function in terms of E-fold as exponential of the E-fold. Here NE is the E-fold at the end of inflation. As we know, the evolution of the inflaton field can be explained in terms of Dan-Gordon equation. So here we see that the evolution of the field depends on the potential explicitly. So if we choose a specific form of the coupling function J phi, we will not be able to obtain this exponential of e-fold form of the coupling function for all the models, which is why we need to construct model dependent coupling functions. So here we have put up a list of slow roll models and their corresponding potential. Using these potentials in this Klein-Gordon equation, we obtain the solution of the field phi. And using the solution of the field phi, we have constructed the coupling functions, which leads to this exponential of e-fold behavior of the coupling function. Now let's see how the power spectra behaves like. As expected, we got nearly scale invariant spectra for helical and non-helical magnetic field and a k-square behavior in the electric field for non-helical case and a nearly scale invariant electric field for the helical case with the amplitude is same as that of helical magnetic spectra. Well, in a nutshell, we can say that if we construct a coupling function using the slow roll solution of the field, we obtain the behavior of a magnetic and electric power spectra like this. So now we will understand the construction of coupling function and the behavior of electromagnetic power spectra for models involving deviation from slow roll. Well, deviation from slow roll leads to features in the scalar power spectra over large scales as well as over small scales. Features over large scales can be produced by introducing a step by hand in the slow roll potential, which has this form. Here alpha is the height, delta is the width, and phi naught is the position where the step is introduced in the potential. Using the same coupling function that we have used in the slow roll case, we obtained the magnetic and electric spectra, which has the similar form as we obtained in the slow roll case, other than there is this step-like features in the spectra in the intermediate scales due to this step in the potential. The next way to generate features over large scales is by using a linear potential with sudden change in slope. We name it as second Starobinsky model, and this sudden change in slope here gives rise to deviation from slow roll, this brief deviation from slow roll is sandwiched between two slow roll regions. Well, how we constructed the coupling function in this case is we have used the slow solution of the field in the first slow roll region to construct one coupling function, and we have constructed another coupling function by using the solution of the field in the second slow roll region. So now let's see how the power spectra looks like for these two coupling functions. So as you can see here, when we use the first coupling function, which uses the solution of the field in the first slow roll region, we obtain nearly scale invariant behavior for both non-helical and helical fields with a suppressed amplitude over large scales for the modes which exit the Hubble radius in the first slow roll region, and a strong scale dependence for the modes which exit the Hubble radius later. Similarly, when we use the second coupling function, we obtain the nearly scale invariant behavior for the modes which exit in the second slow roll region. Now let's move on to the third type of model which generates feature in the scalar power spectrum, and those are by using the potentials with point of inflection. We have used one model that generates features over large scales and two models that generate features over small scales. Now this potential with point of inflection, the field first moves slowly in these potentials, and then once it reaches the point of inflection, its velocity drops sharply, giving rise to a brief epoch of ultra slow roll. And in this ultra slow roll epoch, the field hardly moves. Now, how we have constructed the coupling function here is we have used the numerical solution of the Klein-Gordon equation due to complexity of the potentials, and we have constructed the coupling function using the inverse function n phi, and we have fitted the n phi with polynomials of different orders. For details about the construction of coupling function, you can refer to our recent paper. As you can see here, when the field reaches the point of inflection, there is a sharp drop in the velocity and the field hardly evolves, which leads to a constant behavior of the coupling function. Now let's understand how the power spectra looks like. Well, as we have obtained in the second Starobinsky model, here also we have obtained a nearly scale invariant spectra for the magnetic field and a k-square behavior of the electric field for modes which exit Hubble radius in the slow roll region, and a strong scale dependence behavior for the modes which exit later. And also, as you can see here, the amplitude in the large scale is very much suppressed. So now we have tried to remove these strong features and we managed to iron out the feature for the second Starobinsky model. What we have done here is we have stitched together the two coupling functions in the two slow roll regions using these these forms of step functions. Interestingly, we obtained nearly scale invariant behavior of the magnetic spectra in both the slow roll regions with a burst of oscillations due to deviation from slow roll, and the amplitudes are also in a desirable range. Now, to summarize up until now, I have explained the construction of coupling functions and behavior of power spectra of magnetic and electric field for models involving deviation from slow roll. Well, we had some challenges in doing so, that are we had to construct a coupling function which is extremely fine-tuned. We obtained separation in the magnetic power spectra over large scales, and there is a strong scale dependence over small scales. Now we have circumvented these problems with two field models. The two field models are governed by the action where there is phi is a canonical scalar field and chi is a non-canonical scalar field. Now we have used the form of the non-canonical coupling function which is exponential of b phi, and this when there b phi is non-zero, it gives rise to a sharp turn in the background trajectory in the field space which leads to deviation from slow roll. And due to deviation from slow roll, we obtain features in the scalar power spectra. Well, now varying this action, we obtain equation of motion for the two fields which are coupled. So now I will discuss the models that we have worked with. We have used two potentials, one that generates features over large scales in the scalar power spectra and one that generates features over small scales. As you can see here, we have plotted the evolution of the fields as a function of E-fold. The solid lines represent the evolution for the first model and the dashed line represents the evolution for the second model. As you see here, as one field rolls down the potential, the other remains constant, and when the first becomes constant, the other field starts moving. So we have shown the departure from slow roll by plotting the first slow roll parameter in this plot. So now, interestingly, here also we obtained magnetic and electric power spectra of desired shape and amplitude. This red color plot represents the magnetic power spectra and electric power spectra for the first model. As you can see here, we obtain burst of oscillation over the large scales and near scale invariant behavior later on. For the second model, we have obtained nearly scale invariant behavior over the large scales and a burst of oscillation over small scales due to deviation from slow roll. Now, similarly, for the electric spectra, we obtained k-square behavior with these bursts of oscillations. Now that we circumvented the challenges in the single field model using two field model where we got the desired amplitude and near scale invariant behavior for the two field models, next we'll discuss the constraints on these amplitudes. So we have used a quantity b lambda to constrain the spectra of the magnetic field, and b lambda square is obtained by smoothing the magnetic power spectra over a coherence length of 1 megaparsec with a window function, with a Gaussian window function. Now, using both our spectra, we obtained an estimate of this b lambda, which is of the order of 10 power minus 1 nanogauss, which is well within the constraint obtained in references. Now, let's understand the imprints of these primordial magnetic fields due to two field models on the CMB. Well, as we know that electromagnetic stress energy tensor sources the metric perturbation, and the metric perturbations have their imprints on the CMB. So understanding the imprints of the primordial magnetic fields on the CMB will give us a better understanding of the origin of the seed fields. So we used a publicly available code MagCam, which is developed by Zuka et al. To compute the contribution of the primordial magnetic fields to the CMB. Well, this code assumes a power law form on the magnetic power spectra and computes the CS due to both compensated and passive mode. Now, since this first model has oscillations over the CMB scales, so it is difficult to fit a power law here. So we have worked with the second model, which gives us a nice nearly scale invariant behavior, which is easy to fit a power law with. So providing the MagCam code with the B lambda obtained from the second model and the spectral index from this model, we obtained the temperature and polarization spectra of the CMB. As you can see here, the red color represents the standard CMB spectra, and the green and blue solid lines represent the contributions due to the compensated mode. And the green and blue dotted lines represent the contributions due to the passive modes. Now these green lines are plotted using the parameters obtained from the power spectra for the second model that we have worked with, and the blue lines are due to the contributions corresponding to the upper bound of D lambda obtained today. So with this, I would like to summarize. So the models which involve deviation from slow roll gives rise to features in the scalar power spectra, which improves fit to the CMB data. Well, these models with deviation from slow roll also gives rise to strong features in the electromagnetic spectra. Well, we faced certain challenges in the generation of primordial magnetic fields in the single field model, which are we needed to extremely fine tune the coupling function to iron out the strong features. In the strong features, we obtained scale dependent over the small scales and suppressed amplitude over the large scales. To overcome these challenges, we have worked with two field models, and we obtained amplitude of the spectra. We obtained the desired amplitude of the spectra, and we obtained nearly scale invariant behavior, and these amplitudes are well within the constraint.